Science is a journey. What we know cannot be divorced from how we came to know it. We make progress, we overcome obstacles, we pursue blind alleys, take lengthy detours, make breakthroughs, and are rewarded with fresh vistas. Science books in general talk about what we know, and the better science books talk about how we know that it's true from our present perspective. What's far too rarely discussed, and I think should be, is why we know it, from the point of view of those who carried out the crucial intellectual adventures, who went out into the unknown. What were they looking for? Why did it matter to them? What was at stake, either technologically or in terms of understanding at the time? I start the book with a discussion of the age of the Earth because, for me, the realization of the antiquity of the Earth is the real beginning, even more than the so-called scientific revolution of 100 years earlier. The realization of the antiquity of the Earth is the real beginning of what I call our modern understanding of what kind of place the universe is and our place within it. If we had to name one person more than any other turned physics into the kind of science that we can still recognize today, that person would have to be Isaac Newton. If we had to do the same for chemistry, we would choose Antoine Lavoisier. Lavoisier's eminent responsibilities made use of his scientific background, and he came to include supervision of the tobacco trade, which at that time was a government-regulated monopoly. It was common practice for tobacco sellers to load up their product with ash, and Lavoisier invented an ingenious, very simple test. You would just pour vinegar on the tobacco, and if the tobacco contained any ash, it would fizz. You can try this yourself with vinegar and baking soda. I also discuss some other applications. I talk a little bit about one of the lies we tell our students. We tell our students that different isotopes of the same element, forms of the atoms with a different number of neutrons, therefore different weight to the atom, have exactly the same chemistry. That isn't quite true. Turns out that using this we can look at stalagmites which have slowly grown on cave floors, reconstruct a climate record, and compare that climate record with the history of the time. For instance, the warm period that made it possible for the Norsemen to colonize Greenland, the Little Ice Age, and the rise and fall of, parallel with this, the rise and fall of empires in China, which is where this particular stalagmite was really looked at, and I compare that with other events throughout the world. Towards the end of the book, I discuss what this means for us in the present, the reality, and I fear it is a reality, I wish it wasn't, of man-made climate change at the moment, and the various arguments that are put forward against it, why they're put forward. I feel that's all too obvious. And I actually have a catalogue of 19 separate standard arguments against accepting the reality and acting on the reality of anthropogenic global warming and what's wrong with all of them. The book ends with a discussion of, if you like, the entire history of the universe from shortly after the Big Bang. I'm not clever enough to discuss the Big Bang. I leave that to people like Stephen Hawking. From shortly after the Big Bang, formation of atoms, formation of hydrogen atoms initially, gas clouds, how they come together, the birth and death of stars, the conversion of lighter atoms within the stars into heavier atoms, eventual collapse to form red giants, or for heavier stars, supernovas, scattering of the elements, all the elements that we have through interstellar space, shockwave from a supernova not too far from here, or not too far from where here was 5 billion years ago, triggering the collapse of a local star cloud, formation of the Solar Nebula, what became the solar system, origin of the Earth, which is where we came in.